Well, hi everybody and welcome to my channel L'Art in Physics. Well, in today's video we will talk about cables and specifically about a very important question on cables, which is what is the curve that a cable describes when it's subjected to the action of its own weight? Well, this question can be answered using Newtonian mechanics, but in this video we will use a different approach. We will use variational calculus. Well, we can argue that variational calculus is also Newtonian because it was Newton who first discovered it or invented. But, well, anyways, let's focus on our problem, which is shown on the screen. Here on the screen is a drawing of a cable. The cable, we will assume that the cable is flexible and inextensible. And also, we will assume that the mu, the Greek letter mu, represents the linear density. I will write it here, linear density of the cable, which is basically the mass per unit length of the cable. So our first goal here will be to find the total potential gravitational energy of our cable. For this, we will first analyze a small portion of the cable, a portion of length ds, being ds the length element. So the mass of this small portion, dm, is just simply their linear density times its length, mu times ds. So we can also calculate the potential gravitational energy of this small portion of the cable, why we call it du, which is equal to simply their mass times the acceleration of gravity times their height measured from some reference point. In this case, the height is equal to y, which is the vertical distance between this portion of the cable and the horizontal axis x. So we will have the following expression for the potential energy of this small portion. Okay, I will delete this little arrows here. So that's again the potential energy, the gravitational potential energy of this small portion of the cable. It's worth remembering that the length element of the cable can be written, well, simply using a Pythagorean theorem as dx, the square root of dx squared plus dy squared. This can be rearranged a little bit. If we multiply inside the square root by the dx squared and divide by dx squared, we can rearrange this and writing as follows. And well, we recognize here inside the square root this dy divided by dx is just the derivative of the y function. We can write it more simply, like 1 plus y prime square times dx. So this is the length element of our small portion of the cable. So this allows us to write the potential energy du as mu g y times this square root time dx. And of course, if we want now to calculate the total potential energy, gravitational potential energy of our cable, we just simply need to sum, to add all these small potential gravitational energy. So the total potential energy of the cable, which will equal to the integral of this expression, mu and g are constant. I can take it out from our integral and write the total potential gravitational energy of our cable as the following expression. I will integrate from minus d and d, supposing that minus d and d the coordinate, the x coordinate of the extreme of our cable from where it is suspended, but it's not important. The important thing here is, I will draw a red rectangle here. Is important expression. The important thing here is the following. We know if we want to find the equilibrium position of a system, we can ask first under which conditions the potential energy is minimum. If the potential energy is minimum, then we have a stable equilibrium position. So we can do the same thing here. For which curve y, this potential energy is minimum. And let's note that this potential energy is also an integral of the function y. This is the kind of problem that variational calculus is concerned. And it was first Leonard Euler, if I don't remember well, in 1744, in which year he tackled this problem, and it shown that the solution to this problem is equal to solve the following differential equation. So, as a brief introduction, if we have a general, we call it functional, which is an integral of some function of x, y, and y prime, then the problem to find the minimum of an extreme point of this integral is equivalent to solve the following differential equation. This is now known as the Euler-Lagrange equation. Okay, if we solve then this differential equation, then we can find the function y which minimize our integral. In our case, this integral being the potential gravitational energy. So if we want to apply this equation, we need to first write the expression for this function phi, which in our case is y times the square root of 1 plus y prime square. Okay, this is our function phi here. So let's begin first with calculating the partial derivative of phi with respect to y prime. In this case, it's simply, well, we have here, sorry, a square root. We can write this as follow. If it's more easily sometimes to calculate these derivatives. So it will lead to the following result: 1/2 times 1 plus y prime square to the minus 1/2 times the derivative of y prime inside this binomial, this 2y prime times y. Here we can cancel the 2's and write this expression as follows. Okay, there we have it, our first partial derivative. It can be also convenient to write this as this product. And now we have to calculate the total derivative of this later partial derivative with respect to x. Okay, this is if you analyze this, is a product of, I will interpret this like two functions. The first function is underlined in red, and this second function is underlined in blue. So if we want to take the derivative, we can use the product rule. I first will take the derivative of the red function here. So the x of phi the y prime is equal to first the derivative of the red underlying function, which is equal to y prime square plus y double prime times well, the blue function, which is just simply this expression, plus the derivative of the blue function times the red function. The derivative of the blue function is equal to minus 1/2 times 1 plus y prime square to the minus 3/2 times 2y prime, and now times y double dot, because we are differentiating now with respect to x. Let's not forget that y is a function of x, and this multiplied by our red function. Well, there's a lot of things here that we can simplify. If we simplify this expression, I will write it below here. we can reach to the following result. It's y prime square plus y2 prime. I will now write this exponent as a square root. Okay, minus, and here we will have the following: y prime square y double prime divided by 1 plus y prime square to the 3/2. Okay, that's our first part on this Euler-Lagrange equation. The second part is to calculate the partial derivative of phi with respect to y. Well, it is more easily, because if we take a closer look to the expression of phi, we can notice that the derivative with respect to y is just simply this square root. So our second partial derivative is fairly easy. It's just simply the square root of 1 plus y prime square. And now we are ready to set up the Euler-Lagrange equation. Is this first expression minus the second one. I will write all the expression here together in order to it's more easily to follow our calculations, but I will simplify it. There is a lot of things that can be simplified here. It's just a simple algebraic exercise. I will leave it to you to complete this terms, or to complete the simplification. Sorry, but if we simplify and we multiply this later equation in order to eliminate the denominator here and do the simplifications, we can reach the following differential equation. Okay, so here we are now. I will also draw another red rectangle here. That's our differential equation. How can we solve this? Well, the term y2 prime is a little annoying here, so let's do the following change here. Let's remember that y2 prime is equal to, well, dy prime dx, but this is equal to dy prime over the y times dy over dx. And this is obviously just y prime, so we can conclude that e double prime is equal to y prime times dy prime divided by di. And so our equation can be written as follows: y prime dy prime divided by dy equal to I prime square plus 1. And this later equation can also be rearranged in order to write a separable variable differential equation as following. I just divided by y prime plus 1, and leaving in the left side of our equation only the terms with y prime, and in the right hand side I will write only the y's, the function y. So we can solve this differential equation by separating the variables. How can we do that? Well, here we can do a little change in variable. I will call it I will write in green. Okay, let's call it y equal to y prime square plus 1. So if we set this variable, du is equal to 2 y prime dy prime. I'm just applying differentials here. So we can know that in our left side of the equation can be written as the following expression. I will first here extract the value of y prime is equal to 1/2 u dy prime. That's what we're looking for, because this term, this term here, as I'm correctly, let me check a little bit here. This is a small mistake. This dy, that's sorry. This term here, which is appearing here, is just equal to 1/2 du. That's it. So our left part of our differential equation will lead to the following result: 1/2 du over u, and this is simply, the integral of this kind of expression is the natural logarithm of u, which is equal to 1/2 natural logarithm of y prime square plus 1. And the right hand side is just simply the natural logarithm of y. Okay, plus some constant. I will call it c. So if we rearrange our results, we can write our equation as follows. Okay, so this is simply eliminating natural logarithms here, and this new constant, I would call it c1, is just simply e to the 2c. It's a new constant, and we are almost reaching to our goal. The objective here is to find the equation, the curve y, which is the curve that describes this hanging cable. So we can again integrate this new equation, and if we integrate again this new equation, we can reach the following conclusion. This is just simply y prime equal to the square root of c1 y prime square minus 1. Okay, so we can write this as follows: dy over this square root c1 y square minus 1 equals to dx, and this differential equation can be solved. This is a fairly common integral. We can find it in any decent table of integrals, and reach to the following conclusion: natural logarithm of the absolute value of y plus the square root of y square minus 1 over c1, our constant, equal to c2, a new constant, of e to the square root of c1 x. Okay, where again this c2 is another constant of integration. We can simplify this later equation again, doing some algebra here, and reach to the following result. That's it. We are almost in our reaching our objective here, but we need to do a last step. We need to find the value of these constants of integration, these two constants of integration. Where we can find this constants of integration? Where, if we look again to the problem, I forgot to mention, but important to mention that we are choosing the lowest point of our cable at a height equals to y0 of the x-axis. And also this minimum point implies two things. Where first, y evaluated at x equals 0 is y0. And the second thing is that the derivative of y in 0 is just simply 0, because here is a minimum point. The tangent line here is completely horizontal. If we apply these two conditions to our differential equation, we can finally write the curve of our cable as follows. Okay, and this expression here can be written also in a much more compact form, just simply as y0 times the hyperbolic cosine of x over y0. And this is this hyperbolic cosine function is known as the catenary, the famous equation of a cable suspended by its own weight. So we reach our final objective here. Our goal was to find this the curve that this cable described. Here it is on the screen. Basically, what we do is was to apply the principles of variational calculus. Specifically, we use the Euler-Lagrange equation in order to find the curve of our cable. Okay, well, so this is it. Again, there's a little some algebra that you can complete on some of the steps. I'll leave it to you. It's also very good sometimes to do the work by yourself. If you have any comments, just feel free to let me know in the comment section. Subscribe and give a like if the video if you like it. So that's for now. Bye bye. See you in the next video.